The next thing we're going to look at in tutorial 2 is graphs of base functions. Now you won't find that there's a ton of questions in your assigned questions about this, but it's really important that you understand what identifies each type of functions and what you expect that graph to look like, as well as how you would graph it and what would be the domain. So we're going to start with an equation like, or a function, f of x is equal to 3. What is the first thing that you notice about this equation? So again, f of x is just y. So this is an equation of y is equal to 3. Is there anything weird about this equation versus or function that you don't see that you usually see? Well, let's just see something. So if I was to say, hey, let's choose these values of x and let's solve for y. My equation is f of x is equal to 3. So I'm going to put in f at negative 2 is 3. Well, where do I put the negative 2? There's no x in this expression. Well, you don't. What this is called a constant. This is a constant function because no matter what you put in for x, there's nowhere to put the x, so the y value is constantly 3. So if I was to graph this, I would put a dot at, negative 2, 3, or an ordered pair, and negative 1, 3, 0, 3, 1, 3, 2, 3, and all the way along. Okay, I need lots of dots. Watch, I know I don't. So to connect these dots, ooh, not bad. You're drawing a horizontal line at y equals 3. So what type of function is this? This is called a constant function. So anytime there is no x, so y is just defined as 3, then it is a constant. And if I asked you what is the domain of this function, well, where is it casting a shadow? Or you can think of it now, which I like to think of it more, is what are the values of x that I can put into this equation? Well, since there is no x, I can put whatever I want. So my domain is everything, negative infinity to infinity, or all real numbers. The next function we're going to look at is something like f of x is equal to x. So for this one, when we put in values of x, we'd get f at negative 2 equals negative 2. F at negative 1, we're putting negative 1 in for x, we get negative 1. When x is 0, y is 0. When x is 1, y is 1. When x is 2, y is 2. If I graph these points, I have a point at negative 2, 2, negative 1, negative 1, 0, 0, 1, 1, 2, 2, and so on. So I'm going to put myself a couple more dots just to give my eye somewhere to graph to. Same thing here. I did choose a symmetrical grid, but sometimes I don't. So I'm going to connect these dots. Oh, that was awful. I need software to develop a way to put a line on here. So I'm going to connect these dots the best I can. You guys could use a ruler. Since I don't have the ability to use a ruler on the screen, I put a ton of dots so that even if I have this weird thing in the middle, you know where it was meant to go. But this is a line. We call this a linear function. How do I identify a linear function? Well, there's an x, but the highest exponent on x is a 1. So anything that has a graph of something like y equals x or y equals 2x plus 3, you're always expecting a linear function. What is the domain of a linear function? Well, if you think about it, again, there's arrows going to the left, there's arrows going to the right. So for the graph, I can say the domain is negative infinity to infinity. But again, I'm looking at the equation. Is there anything I can't put in for x? Well, there's no square roots, there's no x's in denominators, there's nothing that would make my equation undefined for any value of x. So I'm going to say again, the domain is everything, negative infinity to infinity. All right, let's try this next one. Now, you're welcome to pause the video and kind of try these on your own, but I'll just keep going. So again, we're putting in values of x. So for this one, I'm putting in negative 2, and now my equation is squaring it. So negative 2 squared is 4. Negative 1 squared is 1. 0 squared is 0, 1 squared is 1, and 2 squared is 4. If I go to graph this, I'm going to start at 0, 0. From this point here, I'm going to go over 1 and up 1, over 2 and up 4. Now I always like as many points as possible, but I can't fit it. I was going to say over 3 and up 9, but the grid only goes to 8. So that's as far as I can go. So I'm going to connect my dots. And does anybody know what this shape is called? So this is a graph of a parabola, but it is called a quadratic function. So it's a quadrat. All of a sudden I'm doubting my spelling. Quadratic, spilt this a million times. Quadratic equation or quadratic function. Okay, and it's a graph of a parabola. What makes this a graph of a parabola, or what makes it a quadratic function, is that the highest exponent is 2. So again, another example of a quadratic function could be something like 3x squared plus 2x minus 1. But again, the highest exponent is 2. And when the highest exponent is 2, I'm expecting this parabolic shape or quadratic function. What is the domain? Well, what was I doing to x? I was squaring it. There's nothing I can't square as long as it's a real number. So again, it's negative infinity to infinity. All right, this next one, this is y equals x cubed. So whatever I put in for x, I'm going to cube it. So this is going to be y equals negative 2 cubed, which is going to give me negative 8. Negative 1 cubed is negative 1, 0 cubed is 0, 1 cubed is 1, 2 cubed is 8. Let's graph it and then talk about this function. A little flattening out there. All right, what type of function is this? This is called a cubic function because the highest exponent is 3. Again, you could have a cubic function like y is equal to 1/2 x cubed minus 2x plus 1, right? As long as the highest exponent is a 3, you are getting this cubic function shape. Now, this cubic function shape can change a bit, but your base cubic function is this guy here. The domain, again, we're just cubing x, so there's nothing I cannot cube, so it's going to be negative infinity to infinity. Our next base function is going to be f of x is equal to the square root of x. Hopefully you're kind of getting the theme with the naming here. What type of function are you graphing? Well, it's a square root function. And when we go to graph this, what happens? Well, let's put in values for x. If I put in negative 4, y is going to equal the square root of negative 4. What's the square root of negative 4? Well, if you type it in your calculator says error because it does not exist, right? It's an imaginary number. Same thing if I go to plug in negative 1. Square root of negative 1 is an imaginary number. I can't graph it. There is no y value for an x value of negative 1. What if I put in 0? Square root of 0 is 0. Oh, there we go. Let's plug in 1. Square root of 1 is 1. If I put in 4, square root of 4 is 2. So let's graph this. So there's nothing up until the point where you hit 0, 0, right? Because you can't take the square root of any negative number. And then the square root of 1 is 1, and the square root of 4 is 2. And again, I wish this graph went to 9 because then I could do 3, but that's okay. This is enough. So this is a square root function, and this is the first function that has a restriction in the domain. If you look at this graph, the graph is going to start at 0 and go to infinity. How else do we know that? Well, we know that we can't take the square root of a negative number. So when you're determining domain, again, this is your base function, but if you're determining the domain of any square root function, you say that the radicand, or whatever's underneath the radical sign, has to be greater than or equal to 0. And then you can write it in this integral notation if you want. So either of those are absolutely fine. All right, this next one is a cubed root function, and what we're looking for here is what's the difference between a square root function and a cubed root function? Well, for this one, can we put in negative values? Well, if I put in x is negative 8, I'm taking the cubed root of negative 8. Can you take the cubed root of a negative number? Yeah, cubed root of negative 8 is negative 2. Negative times a negative times a negative is a negative. Cubed root of negative 1 is negative 1. Cubed root of 0 is 0. Cubed root of 1 is 1. Cubed root of 8 is 2. You'll notice that this is very similar to our cube function. So up here we had y is equal to x cubed, and all we did was we flipped our x's and our y's, right? Which we're going to learn about in chapter 5, that this will be the inverse of the cubic function. So this is a cubed root function, and it looks like your cubic function turned on its side. So we're going to go through a point negative 8, negative 2, -1, -1, 0, 0, 1, 1, and 8, 2. So it's that same shape where it has a little bit of a flattening out when you hit the axis, and then you reach forwards. Now for this one, what we're looking at is the domain. Because we're taking a cubed root and not a square root, you can do negatives. So the domain of this function is back to that -infinity to infinity, or all real numbers, whatever makes more sense to you. All right, last two functions here, and then we'll go on to the domain idea. The next function is this one. Now for this one, the x is in the denominator, so we call this a rational function. When you're graphing a rational function, let's pick values of x and solve for y. Now I've chosen the values to pick. I won't really get you to graph these guys from scratch very much. We're going to talk a lot about rational functions in chapter 3 and 4, and we'll be graphing them more there. This is just sort of to give you an idea of why the domain is the way it is, but we won't be, like a lot of these other graphs, we're going to be doing transformations of, but not this one. Okay, but anyway, when we do this, again, we're giving you values of x and solving for y. If I plug in f at -2, I get 1 over -2, which is -1/2. If I plug in -1, I get f at -1 is 1 over -1, which is -1. If I plug in -1/2, I have 1 over -1/2. Now, 1 divided by 1/2 is the same as 1 times -2, so it'd be -2. I'm going to plug in 0. 1 divided by 0? Undefined. What about 1/2? F at 1/2 is 1 divided by 1/2. 1 divided by 1/2 is 2. Same thing, what happens if I put in 1? I get 1 divided by 1 is 1. And if I plug in 2, I get 1 divided by 2 is 1/2. Okay, let's try to sketch this. So what we're going to do is we're going to plug in these points. We have a point at x is -2. We've got a y value of -1/2. When x is -1, we have a y value of -1. When x is -1/2, we have a y value of -2. And then on the flip side, when x is 1/2, we get a y value of 2. When x is 1, we get a y value of 1. And when x is 2, we get a y value of 1/2. What the heck is going on? Well, what's going on is that a rational function has what we call asymptotic behavior, meaning there's a x value that you approach, but you're never going to be able to reach. We just said that x cannot be 0, right? There's this weird thing where x cannot be 0. So if I draw a vertical line at x equals 0, you'll notice that the graph is kind of, and if I put in more points, like -1/3 a third would be 3, a quarter would be 4, a fifth would be 5. Your graph is going to approach this asymptote. So we call this asymptotic behavior. So the closer you get to x being 0, the closer your y value actually gets to infinity, which is kind of weird. So same thing here, as these values, like -1/2 is -2, -1/3 is -3, -4 or -1/4 is -4, and so on, that this is going to approach this asymptote. So it's almost like your graph like starts coming towards that line it can't be, or the point it can't be, and then it just like takes off. And then on the other side of this is that what's going to happen is that this graph's actually going to do the same thing, and you end up approaching this other asymptote, which we'll talk about a lot more in chapter 4. But just so you know, there's actually also what we call a horizontal asymptote, and it's along here. It's another line that you're approaching and you won't touch, because if x can't be 0, how could we get a y value of 0? So this is y equals 0. And if I tried to get y equals 0, I can't put in x is 0. So how would I ever make this 0? So not only can x not equal 0, but y cannot equal 0 as well, which we don't care as much about, but it's true. So then what we would do is we would approach this asymptote from both directions. So this is the base graph of a rational function. I will not ask you to replicate this again until chapter 4, where we learn more skills to do it. But the important thing I want you to get from this is that when you have a rational function, so something where your x is in the denominator, you're restricted in the values of x because you cannot divide by 0. So the domain of this function would be x cannot equal 0. Now, if you remember that from the last section, this is set notation. This is great as an answer. You could also put the set brackets. You could put x such that x cannot equal 0. I believe this is all the textbook does. If you wanted to go even further, you could say x can be everything, but it can't equal 0, but this is great. If you were going to do that in interval notation, you say the x values go from negative infinity up to 0, not including the 0, and then they start again, not including the 0, and they go up to positive infinity. So either one of those is great. The last graph that we're going to do is this one. This is called an absolute value graph. Now, we do not graph these in Math 50. But somehow either you're expected to know this as a base graph in Math 60. So let's just graph it using x values. So I'm going to put -2, -1, 0, 1, 2. So when I put in x is -2, I get the absolute value of -2. Now an absolute value just makes anything negative positive. So the absolute value of -2 is 2. The absolute value of -1 is 1. The absolute value of 0 is 0. And also, if it's already positive, like the absolute value of 1, it's 1, right? The absolute value of 2, 2. So what does this graph look like? Well, it's kind of like a parabola, but more like a V shape. So you put 0, 0, 1, 1, 2, 2, and it would keep going. So again, because I can't use a ruler, right? You'd have all these points, and then all these points would be over here as well. So instead of a U shape, you get a very pointy V. Ooh, let's see if I can join these. I'm going to try this guy first. So there's the right side. I think I have to come down. There we go. Okay, what is the domain of this function? Well, there's nothing I can't take the square root of as long as it's real. So again, it's going to be negative infinity to infinity. So there's a couple reasons we learn this lesson. One is I want you to be able to identify how many of them are there? One sec. Just want to pull up your formula sheet. So these standard base graphs are on your formula sheet, but I don't give you points. So these are your 7 standard base graphs. Your linear function, which you identify because the highest exponent is 1. Your quadratic function, which you identify as the highest exponent of 2. Cubic, highest exponent of 3. Square root, cubed root, reciprocal. Ooh, I should change that to rational, and absolute value. There is also the constant function, which is not on here. Because the constant function can take so many different shapes. There's not really a base constant function, but your constant function will be something like y equals 2, right? Where you don't have an x value. So we don't really need that one as a standard base graph, but we do need these other 7. And so what's important is that you can identify these 7 to 8 base graphs. But for tutorial 2, all we're going to do with them is identify domains. So by the end of 2.5, we'll be graphing them with transformations, but in tutorial 2, I just wanted you to get the picture of them so that you can identify which ones have restricted domains and which ones do not. So if we look at this first function, y equals 3x minus 2, this is a linear function, and there's nothing I can't multiply by 3 and subtract 2 from. So the domain is negative infinity to infinity. This next function, j of x, is the absolute value of x plus 5 plus 3. So this is an absolute value function. And the domain of any absolute value function is negative infinity to infinity. All right, let's get into the more complicated ones. The next one we're going to look at is this one. This is called a rational function. And for this rational function, we know that denominators cannot equal 0. So 2 minus x cannot equal 0, and we know that because we can't divide by 0. To solve this, I'm going to add x to each side, and I get that x cannot equal 2. And that's a great domain, right? If you just leave it as that, that's fine. If you do like interval notation, you can say it's negative infinity to 2 and then 2 to infinity, but I find that way more work. What about something like this one? Again, the denominator can't equal 0. So if x squared minus 3x cannot equal 0, how do I solve for x? Well, hopefully you're coming from a Math 11 background where you know that anytime you're solving a quadratic equation, one of the ways of solving is to set it equal to 0, done, and then factor. So I'm going to greatest common factor out an x, Maybe I have to trinomial factor, maybe it's a difference of squares, whatever it is. And then I'm going to set each factor, in this case, not equal to 0, and solve. So for me, my overall domain would be the set of x such that x cannot equal 0 and x cannot equal 3. Now I just do it with a comma. I think when I was reading the textbook it said x cannot equal 0 and x cannot equal 3. I'm like, why don't you just write it as one sentence? But whatever. Last couple here. Now we go to our radical functions. And we know that radical functions, as long as it's a square root function, I called it radical in general because they generally are square roots, but this is a square root function. Okay, when you have a square root, and this is not cubed roots, you have a restriction in the domain because you cannot take the square root of a negative number. So x plus 5 cannot be negative, which means it has to be greater than or equal to 0. Solve for x. We get that x has to be greater than or equal to negative 5. Now again, I'm totally fine with this set notation answer. I think the textbook switches to interval notation. So you could say any value greater than or equal to negative 5 would be negative 5 to infinity. This is another radical and specifically square root function. And again, it's what's underneath the radical sign. So it's the radicand that you can't take the square root of a negative. So 3 minus x has to be greater than or equal to 0. Pause the video, solve this guy. I'm hoping that you add the x. If you don't add the x, okay, so for this one the answer is that x has to be less than or equal to 3, so negative infinity to 3. If you didn't move the x, let's say that you moved the 3, it's fine, right? We're going to minus 3 minus 3. I get negative x is greater than or equal to negative 3. Don't forget the rule that if you divide by a negative number, you have to switch your inequality sign. So you'd get x is less than or equal to 3. So just don't forget that rule. And it's only if you multiply or divide by a negative number. All right, hopefully I'm not going too fast. I find without students, I just start talking. Last one is kind of the trickiest one. This one is like a rational function. So it's got an x in the denominator, but it's also a square root or a radical function. It's got both of them in it. So the rational says that the denominator cannot equal 0, and the square root says that you have to take the square root of a positive number. So because this square root is in a denominator, you would say that the radicand has to be greater than or equal to 0, but because it's in a denominator, it can't equal 0. So the only thing you would change is that if your radical is in a denominator, just say that x minus 2 has to be greater than 0 and that x has to be greater than 2. So when you write your interval notation, you would use a round bracket instead of a square bracket. And you'd say x is greater than 2, round bracket, 2 to infinity. So hopefully it makes sense. That was a lot of information. It's probably the longest video of the entire semester, but there's not really any homework from those base functions. The homework will kind of more relate to here, but we will use those base functions graphs again at the end of chapter 2.